everything is closed.
Are you on wait list? Do you have to be on wait list?
Release or am I?
That's why I'm. Sorry. Yeah, I'm sure those filled out way too fast.
The series is like, we knew it was like the hardest part. Should I go here? I can just circle this way.
Yeah, so that's an interesting question. So Newton-Raphson only really looks for a location where the derivative is pretty much close to your starting point. So whenever you use Newton-Raphson and quasi-Newton-Raphson, you're starting from a certain point, and it's going to search for basically the closest max or min, just wherever the derivative is zero. But if you're asking kind of the difference between Newton-Raphson and quasi-Newton-Raphson, they should give you the same answer. Granted, your step size is kind of small enough for everything. But whether it's a max or a min, then you kind of have to kind of test the function and see if that's the case. Just because Newton-Raphson only gives you just where the derivative. Okay, yeah, so based on the starting points that I gave you, it should get you to a min in the one problem, max in the other problem, but. Yeah, in reality, you would have to check. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Good.
Good to hear. All right, it's end of week 12, so one more week until Thanksgiving. All right, or one more week of class, and then the next week is Thanksgiving, so almost there. All right, so plan for today. I want to dedicate today mostly to just going over the Nelder-Mead method. All right, so we started talking about that last time. We have kind of the general kind of idea of how it works. Today we're going to go in detail in terms of all the different steps, all the different operations of Nelder-Mead, and then we're going to go over its implementation in the code as well. Okay, if we have a little bit of time at the end, I'm gonna go ahead and start the next section, which is on constrained optimization, which is what you're gonna need for your final project. Okay. All right. I guess the only real announcement is that remember our midterm exam is gonna be next Thursday. The cutoff for the midterm exam, if you notice from the study guide, is pattern search. So basically, we finished covering everything that you're going to need to know for the midterm on Tuesday. So what we go over today, and then obviously what we're going to go over on next Tuesday, is not going to be on the midterm exam. So Pattern search is the last thing that you're gonna be responsible for on the, okay, at least content wise. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. Okay, so on Tuesday, we started talking about this algorithm called the Nelder-Mead algorithm. So Nelder-Mead is a great method. In fact, it's probably one of the most widely used methods in modern optimization. It has a lot of really great qualities. It's fairly well converging, so it converges pretty quickly, and it has a lot of tools that it can use to get you out of a kind of a bad situation. Okay. In fact, if you end up doing, optimization work after this class or in your professional life, Nelder-Mead is probably going to be the first algorithm that you're going to try for a lot of your problems. So, it's that's generally kind of what people understand. That you have a fresh optimization problem, you don't really know a lot about the problem. A lot of people would say, let's just try Nelder-Mead, let's see if it works. And actually, more often than not, it will work. Okay. And so we're going to go over the unconstrained version here. There's ways to modify this optimization algorithm to account for constraints as well. That's what we're going to start covering next week. But we're going to just start with the unconstrained version. Okay. And so the general idea with Nelder-Mead optimization is that Nelder-Mead aims to maintain and move what's called a simplex towards the optimum point. Okay. So on Tuesday, we discussed what a simplex was. And so a simplex is simply just a polygon in n-dimensional space, okay, where the number of vertices on the polygon is n plus 1. Okay. So we went over two examples, or the two examples that we could actually visualize. So in 2D space, the simplex in 2D space is a triangle. Right? So 2D, that's two-dimensional space, and so a polygon with 2 plus 1 vertices, that's 3. So a shape with 3 vertices is a triangle. Yeah, and the only other one that we could really visualize, at least, in one iteration, is in 3D. So in 3D, we have a shape with 4 vertices, which is a tetrahedron. All right. So the idea with the simplex is the vertices carry a lot of really important weight. So each vertex represents a distinct point in the design space. And so they represent a distinct set of design variables. And if they each represent a distinct design point, that means they're all going to have their own distinct value of the objective function. So this is actually quite interesting. So if you compare this to our previous methods, and so let's take one of the previous methods that we looked at before. Let's say coordinate search, right? And so coordinate search, we're only considering kind of one point at a time, right? So we have our current location, and that current location has a certain values of the design variables, and then we move from that location. Okay. So what's different about Nelder-Mead is that instead of managing just one design point and improving that one design point, we're kind of managing multiple different design points at the same time. Okay. But that gives us that may seem like it gives us a bit more of a headache because there's more to manage, but that it also gives us more information as well. Okay. Because what we can do is that oftentimes what's going to happen is that each of your design points in your simplex, they're all going to have different values of the objective function. So there's going to be a best one, there's going to be a worst one, and then there's going to be a tiered list or a ranked list in between. And whenever you make a ranked list, there's always going to be a worst one. And so, a lot of the logic of the Nelder-Mead optimization is just to look and see who your worst, who the worst vertex is, who has the worst optimal value, and then just kick that person out and form a new simplex from there. Okay. So that's kind of the idea. And so, instead of just managing one point at a time, we're managing kind of a collection, but that collection is going to allow us to give hints in terms of, which direction is the least desirable, which direction is the most desirable, and, we can kind of move the simplex along that way. Okay. All right. Any questions on this so far? This is mostly just a recap from last time. Okay. All right. So Nelder-Mead is really kind of characterized by all the different operations. Okay. And by operations, what I mean is, some way to manipulate the simplex. Okay. Either to move it to a certain location or to rearrange the simplex. Basically, all these operations will affect the simplex in some way. All of these operations with the goal, all these operations have the same goal of moving the simplex towards the optimum point. So we're gonna go over the different operations. So there are three main operations. And then there's kind of an emergency operation as well. So there's kind of a, if all else fails, there's a hidden fourth one. But for the most part, most of your operations are gonna be, 1, 2, or 3. Mostly 1, actually. Okay. All right, so let's go over the first operation. So the first operation is called reflection. All right. So reflection, the way this works is that, between all the different vertices on your simplex, you're going to locate the one with the least optimal objective function value, so the worst point. Okay. So you're going to identify the vertex with the, with the least desirable value. And what we're going to do is we're going to kick that guy out. Okay. Survival of the fittest. I guess survival of the most optimal, I guess you could say. Okay. All right, so after we kick out one of the vertices of the simplex, our simplex is is not going to be complete at that point because we're missing a vertex, and so we need to replace this with another point. Okay. So we're going to replace this point with another one. Okay. Now the question is, where do we put this extra vertex? Well, this new vertex is going to be reflected based on the location of the previous point that was just removed and all the other points that are still there. Geometrically, it looks like you're kind of putting a point at the other side of a mirror image. Okay, that's why we kind of give it the name reflection. Okay, so it's a little bit easier to draw it than it is to describe it with words. So let's go ahead and draw it. Okay. So here's what a reflection operation looks like in 2D. That is the extent of my artistic ability. Okay. So let's say that we had an original simplex that looks like this. So in 2D, remember our simplexes are triangles. So we have point 1, point 2, point 3. All right. And so of course, at each of these vertices here, we have the respective objective function values. So we have F1, F2, and F. Okay. All right, so between these points, let's say that F3 is the least desirable of the bomb. So F3, let's say that we're doing a minimization problem. So F3 has the highest or largest magnitude value of the objective. Okay. Okay. So we want to kick out F3, okay, for point 3. And so if we kick out point 3, then we have to redraw our simplex, okay? Okay, so we want to generate a new point, point 4, right? But now the question is, where do we go from here? All right, so generally the logic behind the reflection operation is that, we know that F3 is the worst one. So we want to move the simplex as far away from F3 as possible, within reason. So we don't want to take, giant steps here. Okay. So what if we do this? And so if we look at the two remaining points in the simplex here, right? They form a line, right? In 2D, they form a line. So what if we take the point 3 and we find its mirror image across that line? So we basically imagine that the line is a mirror, and we find the mirror image of point 3 across that line. Okay? What we say basically is that, we take point 3, we draw a line that's kind of perpendicular to it, and we keep going on the other side of the line. Okay. So this new point 4 moves, we moved it in the opposite direction as point 3. And so we can redraw our simplex now. Okay, so now that we have 3 points again, I'm gonna go ahead and connect points 1 and point 4, and then point 4 and point 2. Okay. So now the simplex, we have a new one where ideally point 4 will have an improved value of the objective function. Okay. All right. So that's the logic of reflection. So reflection is one of the main ways, or one of the main operations that you're going to be using in Nailed-or-Beat, right? And so you can hopefully see that, through successive, reflection operations, the simplex will kind of gradually kind of move itself. It almost kind of looks like kind of an itsy bitsy spider kind of thing where, 2 of the points are fixed, you move one of them, and so the whole thing kind of pivots, and the whole thing kind of pivots again. And so, eventually through successive reflection, you're going to move closer to the object. Okay. All right, any questions on kind of the logic of the reflection operation? Okay. All right, so and hopefully, what you see here is that, all 3 points in the simplex were participating in this operation, right? It wasn't just that we deleted point 3 and we just found a new random point, right? The location of the new point 4 is based at least partially on the locations of the other 2 points in the simplex. Okay, so all the points in the simplex kind of work together for this. Okay. Okay. So that's kind of the geometric interpretation of reflection, but when we go to implement this in the code, we can't draw a picture from MATLAB. We actually need to put in a formula for MATLAB to implement this course. Okay. So let's see what the or let's see a formula for the reflection. Okay, so we have a formula of xr, this is the coordinates of the new reflected point. This is equal to 1 plus alpha. Alpha being a tuning parameter or a coefficient that you can modify, and we'll talk about kind of what alpha means in a second, okay? Multiplied by x naught, okay? So this x naught here, this is the centroid of all the simplex points in the previous simplex. Okay, except the worst one. All right. So whatever points are still remaining in the simplex, the ones that you're not going to remove, you find the centroid of that, and then that factors into this equation. Okay. Minus alpha multiplied by x h. For this x h right here, this is the coordinates of the worst point in the simplex. So this is the one that you're going to remove. All right, so that's our formula for reflection. So, the coordinates of the new point is equal to 1 plus alpha multiplied by the centroid of the points that are still remaining in the simplex minus alpha times the coordinates of the worst point. Okay. All right. And so for XO there, let's write a formula for that one just because that'll be useful as well. Okay. So XO, previous equation, this is simply just the centroid of all of the other points. And so, one simple way is just do 1 divided by n, okay, multiplied by summation I equal to 1 to n of xi, okay. Right, so you basically just take the average of all the coordinates of all the other points in the simplex, but you want to make sure that you skip the worst one. And so that's pretty simple to do in MATLAB. And so you can just either take an average, or you can take a mean, or you can use a summation, divide by n. So there's lots of different ways that you can do this in that. Okay. And n, remember, n is the number of design variables here. Okay. Or excuse me, n is the number of design variables. Okay. Now let's talk about the alpha parameter, because alpha is kind of an interesting one here. Okay. So from the geometric interpretation up here, we can see that, when we do a reflection, we move the second point, on the other side of the simplex from the worst one. Okay. I didn't really say anything about how far we should go, right? Kind of the assumption here is that, this distance here between the old point and the previous point and this distance are the same, right? But it doesn't have to be. So you can actually, tell your Nelderby to be more aggressive and then actually put this 0.4 out here as well, okay? Right? You can either put it further away or you can put it closer to the simplex as well, right? So that's actually something you have control over. And the way that you control that distance is through that alpha parameter. Okay? All right, so the alpha parameter affects how far the new point is from the rest of the simplex. And generally, there's three kind of regimes that you can pick, based on how aggressive or how safe you want your algorithm to be. Okay. So if you pick a value of alpha that's less than one, okay, that's generally considered to be kind of a safe option. And so when you pick an alpha less than one, your new reflected point will be placed close to the simplex. And so with the safe option, we've kind of talked about this in terms of the other algorithms. With the safe option, you're less likely to run into problems. But it's also going to take more iterations to converge. Okay. If you're doing an optimization on a new problem that you really don't have any idea how it's going to work out, having an alpha parameter less than one, is not a bad idea. You don't want the algorithm to do kind of weird stuff. All right, and so you set the alpha parameter equal to one, the distance between the simplex before the new point is the same as the old point. So this is kind of the default, or this is kind of the neutral, the neutral choice. Okay. So it kind of gives you a balance of a little bit of aggression, but playing it a little bit safe as well. Okay. And of course, if you set this parameter greater than one, that puts the new point further away from the simplex. So this is the more aggressive option. Okay. So maybe you want to converge faster. Maybe you know a bit about the problem. Maybe you know that you can go a bit faster. Maybe you have a situation where your objective function is very expensive to compute. So you don't want to, you don't want a slow algorithm. So, so you're not waiting for years. Those are all kind of, decisions that you kind of have to make on a case by case basis. Okay. And even though I say alpha greater than one, generally people don't set the alpha parameter to be like 100 or something like that. So when I say greater than one, usually it's like 1.5, 2, or 2.5, something like that. So nothing too crazy. Okay. But if you set alpha greater than one, you kind of run the risk of kind of skipping over the optimum, kind of making your simplex kind of do some kind of weird things. You're more likely to kind of get stuck because you're not able to find kind of a good place to land in. So, more weird stuff can happen when you're a bit more aggressive. Okay. It's a risk and a reward type. Okay. Any questions on this so far? Okay, good. All right, so reflections are one of the main operations that your nilder read can do, probably the most common one that you do. Okay. Generally speaking, this logic of taking your worst point, taking it out and moving away from it, that generally leads to improvements on the objective function. But it doesn't always work because there are some objective surfaces that kind of have a weird shape. Okay. In particular, let's consider a situation where the reflection operations kind of get stuck within a valley. So for example, let's say that you perform a reflection operation, okay, and so you compute your new point. But your new point, let's say that it has, either the same objective function value as the one you kicked out, or it has an even worse. And so what's going to happen in this situation? So, if you just do just a straight up reflection, then your simplex will accept this new point. But then when it goes to run the reflection again, it's going to kick out that new point. Okay. Right. And so you're going to kick the new point out, and then you're going to perform a reflection. But if you reflect again, you're going to be basically right back where you started. Okay. And so you're going to reflect again, end up back in the same place, reflect back in the same, and you just keep going back and forth. Okay. This is especially true if your alpha parameter is one, at least one or greater than one. So this can happen. And so when we say, or when this happens, what we're saying is that your objective function or your simplex is stuck in a valley. Okay. Okay. So what can you do in this situation? Well, you can try something a little bit drastic. And so, what you're kind of hoping for in this situation is that you're kind of just stuck in just kind of a really small wrinkle in the objective surface. And so maybe if you do something drastic, it kind of gets you out of it and you can kind of continue on your way. Okay. So one strategy that you can do is you can perform a reflection, but instead of kicking out the worst point, you kick out the second worst point. Right? And so this will kind of adjust how your new reflection point is done. And so if that's good enough to break you out of the valley, then you can kind of continue on from there. Okay. But sometimes even that won't work too. And so if that doesn't work, and so if you're not basically if you're not able to get out of a location, if you're completely stuck doing reflections, then you have to try something else, right? And so that kind of introduces our second operation, which is called contraction. Okay. So one possibility that if you're stuck doing reflections, that you may be just completely stuck in a valley in a weird point. Or another possibility is that maybe you're getting closer to the optimal value and you kind of need to zone in on it. Okay. So contraction operation basically aims to make the simplex smaller to hone in on a particular point. So the way that you make a shape smaller is that you take the vertices and just kind of bring them closer together. Okay. All right. So a contraction operation is never done on its own. So a contraction is only done after a failed reflection. Reflection, ideally, is the operation you want to do the most, because that kind of results in kind of the biggest change in the simplex. But if reflection is not going to work, then you've got to try something else, right? So contractions is the way that we do this. Okay. Okay. And so, the way that we contract is that we actually only contract one point at a time. So we bring one point closer to the kind of the centroid of the simplex. Okay. So the formula for that, and we have xc is equal to theta multiplied by xh plus 1 minus theta multiplied by xo. Okay. So this formula for contraction looks quite similar to our reflection, our reflection equation here, but of course, there are some differences here. Okay. So xc here, this is our contracted point. So this is going to be the new point that's going to be in our simplex. xh here, this is the current worst point in the simplex. And this XO has the same interpretation as before. This is the average of all the other points in the simplex except for the worst one. So you basically take the worst point, compute a new one that's closer to the simplex, and just hope that this leads to an improvement on the objective function. Okay. All right. And so visually, it might look something like this. Right. So let's say we have points 1, 2, and 3. So let's say 3 is the worst point. And so we want to cross out 3. And we want to make a new point, not reflected across the simplex, but just brought closer. Okay. So this would be point 4. You can see here that it's kind of existing on this line that goes towards the rest of the simplex. And then our simplex has gotten smaller by comparison. Okay. All right. So contraction works really well when you're getting close to the optimum. Okay. And so the hope is that the real optimum kind of hopefully it's within the simplex right now as it stands, and you're kind of bringing that point closer to that optimum. And so the hope here, just like with reflection, that by producing this new point, this leads to an improvement of the objective function relative to the point that we just picked out. All right, any questions on this? Okay. All right, so ideally, if you're getting close to the optimum, then what's going to happen is your simplex is going to contract multiple different times across all the different vertices. Okay, and so eventually, if you contract enough, your simplex is going to become really, really small. Right. So hopefully, eventually, you eventually contract and you hone in on that optimum point. Okay. And that's actually our convergence criteria for the Nelder-Mead optimization too. Okay, so Nelder-Mead, we say it converges when all the simplex points are really, really close together, and they all basically give you the same value of the objective function. So I wanted to mention that here we have one more, we have 1.5 more operations to go, but I wanted to mention the convergence criteria because usually you check for convergence after a contraction operation. Okay. So we've gone over 2 operations. We've gone over reflection. Reflection is kind of our default action. So if we're not really sure what to do, reflection is kind of a good one to go with. And now we have contraction. So contraction is what you do when a reflection operation doesn't go well. Okay. And so if you reflect, you don't find an improvement, then you contract. Okay. What happens when your reflection operation goes really well? Right, so that's gonna lead us into our third operation, which is called expansion. So expansion, based on the name, you could see that it's the opposite of contraction. So the idea of expansion is to make the simplex even bigger than it was before. Okay. And just like contraction, expansion occurs after a reflection operation. Okay, but the circumstances is different. And so we do as an expansion. When let's say our expansion, or excuse me, we do an expansion when our reflection operation leads us to a new point, and that new point is the new best point in the entire simplex. So not only is it better than the old point that we just deleted, but it's better than all the other points currently in the simplex as well. So in other words, our reflection not only led to an improvement, but it's better than everyone else already in the simplex. And so the logic here is that we did a reflection, we found a really good improvement. So let's kind of keep going in that pathway. So that tells us that the direction that we're going from that reflection is really, really good. So we should keep going. All right. So visually, it looks something like this. Say we have points 1, 2, and 3. Okay. Once again, let's say that 0.3 is the one that we're gonna kick out, okay? And so after a reflection, and we end up with 0.4. But then let's say that when we compute the objective function at 0.4, it's not only better than 0.3, but it's better than 0.1 and 0.2 as well. So that means we should keep looking in this direction. So we should expand our simplex into that direction further. Okay? And so in the expansion, right, so we're going to keep going in this direction. Develop a new 0.5, okay? So now our simplex is going to be comprised of 0.1, 0.2, and 0.5. Five here, this is our expanded point. All right. So let's write out our formula for expansion. So our formula for expansion is XE. This right here is the coordinates of the expanded point. Two. Gamma. Oh, I think I forgot to define the contraction parameter beta up there too, but you know, beta kind of has the same interpretation as alpha, which kind of has the same interpretation of gamma too, right? So with Nelder mean, you have kind of three parameters that you need to set beforehand that affect the algorithm. You have alpha, the reflection coefficient, beta, the contraction coefficient, and gamma, which is the expansion coefficient. Okay. So XE here is equal to gamma times XR, where XR here, this is our reflected point. Remember, expansion is only done after a reflection, so we do have the coordinates of a reflected point, okay? So in the example that I did above, point number 4 there, that would be XR, okay? Plus 1 minus gamma multiplied by XO. And this XO here, this has the same kind of interpretations before. This is the centroid of all the other simplex points of the ones that, you know, that kind of stayed stationary. So all these formulas look similar. You know, I realize that. So the reflection formula, the expansion formula, and the contraction formula, you know, they all kind of have, you know, they all kind of look similar. But you know, make sure you kind of capture all the subtle differences between them. All right. Any questions on that? Okay. So those are the three main operations of Nelder-Mead. In fact, you know, you can write the Nelder-Mead algorithm with just those three. There's an extra fourth one that I want to discuss with you too. This fourth one isn't typical. So you know, there are some implementations of Nelder-Mead that don't include this fourth operation, but it can be really useful. Okay? Okay, so a fourth operation here, and I like this one because this is the operation that really helps you get unstuck, right? So if you get stuck in kind of a particularly nasty location in the design space, you know, sometimes no matter what you do, no matter what reflection or contraction you do, you know, you can't really get out of it. So fourth is kind of like a panic button you can push to kind of get you out of a bind. So the fourth operation here is called the shift. Shift is the only operation here that moves more than 1 point at a time. So all the other operations, reflection, contraction, expansion, they only move 1 point. Shift is going to move multiple points. And so the idea is to shift your entire simplex towards one direction in the hopes that you kind of get unstuck from wherever you are. So a shift is only executed when a contraction operation does not lead to any improvement. And so you try it, and so you can kind of think of all the logical steps that it takes to get here. So you tried a reflection, that didn't work. You tried a contraction, that didn't work. Maybe you try a reflection on the second worst point, that didn't work. You try a contraction on the second worst point, that didn't work, right? So nothing has worked so far. And so a shift is kind of your ultimate panic button. Okay? So the idea with the shift is to move all the points in the simplex towards the current best point. Current best vertice in that simplex. Okay. So the formula for this is actually quite simple. And so, to perform a shift, you need to keep track of, what's your current best point in the Nelder-Mead simplex, okay? And every other point, you're going to move towards that point, right? So the formula here is xi. With xi here, this is the new simplex point. Okay. Is equal to 1/2 xi. Okay, so I know I'm using xi on both sides of the equal sign here, so it can be a bit confusing, but I wanted to illustrate that this is the same point on both sides, right? So you're taking that point and you're moving it to a new location. Okay. And in fact, this is kind of how it's implemented in code too. So in code, you're basically doing an update operation. So you say like variable is equal to variable plus something else. Okay. Is equal to plus x on L. So this XL here, this is the current best point in the simplex. Okay. And again, with the shift, you're not going to do it for just 1 point. You're going to do this for all the points except for the best one. Well, technically you could do it for the best one too, but you're just going to end up in the same place as you were. So I like this adjustment to Nelder-Mead because it's a good one, especially if you have a troubling kind of objective function. It gets you out of a mess sometimes. Okay. But this is not tradition. So if you just kind of call Nelder-Mead from MATLAB or you call Nelder-Mead from Python, it's probably not going to have this operation. But I like to include it just because it's a good panic button. It's really useful if you're gonna use an elder mead for your final project as well, because the final project has a lot of pitfalls from what I. All right, any questions on the shift before we jump to the code? Okay, all right, so let's do an example here, the final example. So I think we've done this problem so many times now, but this will be the last time that we see it. Okay, so let's minimize the following functions. We have a two-dimensional function. F of x1 comma x2 is equal to x1 minus x2 plus 2x1 squared plus 2x1 x2 plus x2 squared. Okay. All right, so we're going to use Nelder-Mead, and so we need the locations for our starting simplex. So we're in two-dimensional space here because we have two design variables, and so that means our simplex is going to have n plus 1, 3 points. Okay. All right. So to avoid any confusion with 1, 2, I'm going to call the points XA, XB, and XC. So say XA here is 4.0 and 4.0. Right? XB 2, 5.0, 4.0. Okay. C is equal to 4.0. So we're starting with a fairly closely packed simplex. Okay? And so if you look kind of on the x1, x2 plane. Okay. Our simplex is kind of starting like this. XA, XB, which is to the right of it. XC, which is right above that. So that's what our starting simplex is going to. Okay. Additionally, I'm going to give you the values for each of the parameters. So for the reflection coefficient, let's just use the default. So we're going to use an alpha value of 1.0. Let's use a contraction coefficient beta. Let's use contraction coefficient of 0.5. Okay. And then for the expansion coefficient, let's say that that's going to be equal to 2.0. All right, and then the last thing that we need, I think I've kind of glazed over this for the previous example, but we also need a variable for the convergence parameter. Okay. So remember, Nelder-Mead converges when all the points are basically close together, and they all give you the same value of the objective function. Okay, so the tolerance that we're going to use for that is we're going to give it the variable name epsilon. And we're going to set that to 0.2. Okay. So basically, once the values of the objective functions at all 3 points of our simplex are within 0.2 of each other, then then we can say that we can stop. Okay, all right, so let's go ahead and jump into the code. So let me go ahead and share my screen here. I think that'll take us right up to the end of class. And I forgot to start math. Make sure I have the code downloaded. So this example is available to you on Canvas. So it's UNLP example 5 and Nelder-Mead. Okay. Probably the most complex code that we have. In terms of the number of lines. But you'll see kind of all of the formulas that we went through. You'll see all the different operations implemented in MATLAB as well. And so you'll kind of see the whole picture too. Okay, we're done with pattern search, we're done with coordinate search. Now we're looking at okay, let's see how many lines there are. Oh, it's not terrible. There's about 131 lines. Okay. And a lot of it is kind of in this early section too. Okay. All right. So let's kind of read this code from the top and kind of see how the logic is given. Okay. Threshold is 0.2. Okay. So first thing we see here is that we have a maximum number of iterations. Okay. So you've probably seen a couple different styles of me implementing these algorithms, right? So there are some algorithms that I've defined with a while loop, and so with the while loop, we basically say we're just going to keep going until we converge, and we kind of have the confidence that we are going to converge eventually. That's not true all the time. So this is kind of a safer way to implement an optimization, where you set kind of an upper limit in terms of how many function evaluations you want to do, how many iterations. So that by the time you reach the end of that, then you exit. Okay. Nelder-Mead kind of traditionally is implemented with this style because even with all the safeguards, it is still possible to get stuck. And if you get stuck, you don't want your program to move endlessly, and so you want to set an upper bound for that. Okay. Next, we have little n. Little n is the number of design variables for this problem, which is 2. Okay. Okay. Now, this is where it gets kind of interesting. So remember, in Nelder-Mead, we're managing not just one point at a time, we're managing 3 points at a time, right? Or in this case, the 2D problem was 3 points, okay? We need to keep track of all 3 of those points at the same time. Right? So the way I'm doing this here is I'm creating a matrix called xi that's going to store all of our simplex points, okay? So if you look at this matrix is 3, 2. So that means it has 3 rows and 2 columns. Okay. So it looks something like this. Right. And the way to read this matrix is that the first row of this matrix is going to be XA. That's going to be the first point in our simplex. Second row is going to be XB. And third row is going to be XC. Okay. And each simplex point is going to have two values here, right? Because you need a value for X1 and a value for X2. So that's how we're going to store it, and that's how we're going to kind of keep track of it during the algorithm. Right? So kind of understanding this xi vector here is kind of key to this whole operation. So not only do we need to know the values for all the design points in the simplex, we also need to keep track of their objective function values as well. So I'm creating another vector here, fi. So fi is a column vector with 3 rows and 1 column. Okay. And so the 3 rows in this matrix are FA, FB, and FC. Okay. All right, and so these values are going to be correlated to the objective function values in the vertices matrix that we had over here. All right, so next section of the code here, we define alpha, beta, and gamma. So those are the Nelder-Mead parameters that we discussed before. Okay. We have our convergence threshold here, which is just 0.2. And now these next set of lines here, this is computing. Well, first of all, this is establishing our initial simplex. And so you can see our initial simplex here. We have 4, 4, 5, 4, and 4, 5. Okay. And we need to compute the objective function at those values as well. Right. So we're computing the objective function at our initial XA. We're computing the objective function at our initial XB, and then our initial objective function at our initial XC, okay? And so we're saving those values in our FI vector, and we're saving the coordinates in our XI vector. Okay, and if you've never seen this before, if you've never seen, if you've never seen colon notation in MATLAB, that basically means that we're setting an entire vector within that matrix, right? So remember, this XI matrix here is a 3x2 matrix. Right, where each row in that matrix is going to represent a different design point or different vertex in our simplex. And so what this is saying is that we're going to be setting the first row of this matrix, and every single column that's gonna be equal to x1, which is this 4,4 vector here. Okay. So it's just kind of a shorthand, kind of fast way to assign a vector into a matrix. Okay. All right, another thing that we, that's kind of interesting here too, is that, we need to keep track of whether or not we're going to perform an expansion, a contraction, or a shift, okay? Because remember, we don't perform an expansion, contraction, or shift every single time. It kind of depends on what happens with the reflection, okay? So for sure, we're going to perform a reflection each time, but depending on the results of that reflection, we're going to, set these flags to true, okay? I initialize all these to false just because, we're gonna start with the assumption that, we're not gonna perform, any expansion, contraction, or shift. Okay. Okay, so let's jump into the loop here. Okay. Okay, so we jump into the loop, and so we have 4j is equal from 1 to n. So you can see we're going to do at most big N iterations. Okay. First thing I'm doing here is I'm checking the convergence. And so, remember what we say, the algorithm is going to converge once all of the objective function values in our simplex are sufficiently the same, right? And so what we can say is that if we compute the standard deviation, so STD, I know STD stands for something else, but in this case, it's standard deviation. If the standard deviation of our objective functions values, Fi, if that's less than the threshold, then we've converged. Okay, so then we basically break out of the algorithm. Okay, but if we're not converged yet, then we go ahead and proceed with the other operations. Okay. All right, so first one is reflection. So in order to perform a reflection, we need to identify the worst point in the simplex, right? And since for this problem, we're doing a minimization, then the worst point is going to be whichever point has the maximum objective function value. Okay, so we use the built-in function in MATLAB called max, and so max will give us the value of the worst objective function value as well as the index, so that we know which point to kick out. Okay. All right. Next thing we're going to do is we're going to compute the centroid of all the other points. Okay. And so remember, no matter what operation that we're going to be doing, we need to compute this XO variable here. Okay. So we are doing a summation. So we're summing up all of the points except for the worst one. Okay. So the way we're doing this is we're doing the for loop from k is equal to 1 to n plus 1. Okay. If k is equal to the worst index, remember worst index, that is the index of the worst point in the simplex right now, then we just skip over that one. So we just say continue. Okay. If not, then we sum these up. And then at the end, we divide by n to compute the centroid. Okay. So by the time this code finishes here, we have the value of the centroid of the rest of the design points in that simplex. Okay. Okay. All right, so from there, we're going to do our reflection. So if you look at this formula here, this is exactly the same as the XR formula that we went over in the lecture. Okay, so you have 1 plus alpha times XO minus alpha times the point with the worst objective function value. And then we evaluate our objective function at this new. Okay. Okay. All right. So now we need to check. So now we're going to check to see if our reflection led to an improvement. And so it led to an improvement if our new reflected objective function is less than our previous worst value. Okay. And so if that's true, then we save this point and we just continue on. Okay. Now we need to check. So now that the reflection's done, right? And ideally we've obtained a point that's better than our previous one. Okay. At this point, we're going to check to see if we want to do an expansion. Right, so remember, we do an expansion whenever our new reflected point is better than all the previous points before. Okay? So what we're going to check to see is that if FR is less than the minimum of FI, then we're going to set this flag equal to true. We're not going to perform the expansion just yet, but we're going to remember that we're going to do an expansion. Okay. All right. Next thing we're gonna do is we're gonna check to see if we want to do a contraction. Okay. All right, if we want to do contraction, that means our FR here is worse than the previous one, or if it's still worse than all the other ones. Okay. And so that's kind of what this if statement kind of shows here, right? And so if that's true, then we set perform contraction equal to true. Okay. Okay. So at this point in the code right here, our reflection is done. And we know if we want to do the expansion or contraction. Okay. All right, so here's where these flags kind of come into play. So if we set this perform expansion flag to true, then we do the expansion in here. Okay. And so the code inside this if statement here performs the expansion. And so you can see here that this formula for XE, this is the same formula that we had in the lecture for the expansion point. And then we're going to compute the objective function at this point as well. Okay. We want to check to see if this is an improvement. So sometimes an expansion doesn't lead to an improvement. And so if that's not the case, then we kind of just leave it alone. Okay. And then this is really important. So just so that we don't perform an expansion on the next iteration, we have to reset this flag to false. All right. And so remember, we only execute this code if we've identified that we want to perform an expansion. Okay. Okay. If not, if we didn't perform an expansion, then we may perform a contraction as well. Okay. So if we want to perform a contraction, then we go inside this code here. So we have our formula here for XC. So this is the same as it was in the class. We have our new objective function value. Okay. And we're going to check to see if this led to an improvement. And so if this led to an improvement, then we're good. But if not, then we're going to perform a shift. Okay. And so we have our shift flag here set to true. And once again, now that we're done with the contraction, we're going to set the contraction flag to false. All right. And so, if the contraction did not lead to an improvement, then we perform a shift. And so you can see here, this is the code for the shift. We have a for loop in here because we need to improve every single point with the shift, except for the best one. Okay. And then we set this flag equal to false here. So there's I think more than any other algorithm that we've gone over so far, this has the most, I would say, kind of programming type of stuff because we have these flags. Okay. But hopefully, this following this code right here kind of follows kind of the same logic that we talked about in the class. Okay. But you can see, even though it's a lot of lines here, it's fairly elegant, and so the lines aren't particularly long. And hopefully it's kind of easy to kind of follow the logic, right? All right, any final questions on the code here? Okay, all right, so that's all we got time for today. So I know I went through this a little bit fast. And so if you're interested in using EGME for your final project, we can definitely go over this again. But on Tuesday, I'm going to start a new topic. So on Tuesday, we're going to start with constraint optimization. Which is kind of the last thing that you need before for your final project. So we'll start that on Tuesday. Obviously, we're going to have the midterm exam and the Thanksgiving break, and then we'll pick that up after we come back from Thanksgiving. Okay. All right. So thank you guys for coming today. I hope you guys have a good weekend. Best of luck studying for the exam. Remember, I have office hours open for people who get questions on that, and I will see you guys next week.
Professor?
Yes.
A quick question. So for the exam, for the 1D questions, would you say that questions, I think it's 3, the last few on the first homework would be a good starting point? And I was just curious, so are we gonna have to know how to do the random number generator on the test or no?
If I ask you to do something with a random method, so like Monte Carlo or I'll give you the random value. So you don't have to have a random number generator in your head. So So, for example, so let's say I give you a 2D problem, say to do Monte Carlo, I say, you have two design variables, I say, let's pretend the random number generator gave you, I don't know, 0.3 and 0.7. And so you would use those to compute the values of the design variables.
Perfect. Okay, and then for the 1D, are we just solving this by hand, or are we like supposed to kind of come up with code that would solve it?
Mention this, I'll send an announcement, but for the 1D problem, I'm gonna limit it to either dichotomous search or Newton-Raphson. Interpolation methods, it takes a little bit too long to do on the exam. So I'm gonna limit to either dichotomous or Newton-Raphson.
Perfect. Thank you so much.
Super flat.
Either dichotomous search or Newton-Raphson for the 1D problem. Newton-Raphson. Yeah, so I think that's the second problem on the current homework. Yeah, that used to be part of the previous one. So the main thing is that if problem 4 on homework 4, you should know how interpolation methods work in general, but I'm not going to give you a problem like that on the test because it's just way too time consuming. Yeah, not like problem 4 on homework 4.